Hi there. So my name is Zach Wartell. I'm an associate professor at University of North Carolina at Charlotte in the Charlotte Visualization Center. And this work was done by my just graduated PhD student, Isaac Xiaoyu. And we also had contributions from our colleagues Wenwen, Xiaoyu, Yang, and Bill Ribarsky. So I'll be talking about the effects of stereo and motion cues on perception of a volumetric data set under two different experimental tasks. So volumetric data, of course, gets used in a lot of different types of 3D visualizations, especially in scientific visualization. You have, say, 3D weather simulations or raw Doppler weather radar, which can be visualized in 3D. And of course, you have lots of 3D medical scans as well. And if you compare this to, say, visualizing and interacting in 3D interaction techniques with surface data sets, you have additional complexities with volume data in the sense that you have multiple, possibly arbitrary numbers of layers of transparency, a lot of different occlusion depending on the opacity function that's applied to the volume rendering, which leads to a lot of ambiguous spatial data structure. And in the paper, we talk about and review a variety of techniques that have been used to sort of deal with this type of issue in volumetric data, including interactive manipulation of transfer functions, illustrative visualization, but our focus is going to be on techniques that and studying the effect of stereo and motion parallax from head tracking. So the particular data set that sort of inspired our artificial data set was this image from Moore et al. In 2004. This was an MRI scan of blood vessels. And in this particular paper, they were pointing out that in this center area, the circular vascular structure appears to be, this circular one appears to be in front of this one that goes diagonally from the top left to the bottom right. But in fact, the actual depth ordering is reversed. In part, this was due to their particular rendering technique of maximum projection intensity. But these types of situations of ambiguous spatial structure can occur in other types of rendering as well. So our goal was to come up with an experimental protocol where we could do, say, 100 to 200 experimental trials, and that from trial to trial, the participants who are looking at the data set could not learn from one trial to the next the spatial ordering of the sort of abstract representation of those blood vessels. So what we basically did is we chose to come up with an artificial data set where we could randomly permute the ordering. So essentially, you can imagine we had 6 different cylinders rendered in a volumetric rendering. Their order was randomly permuted from trial to trial in terms of their depth order, and also the size of the cylinders is randomly permuted so that you couldn't use the size of the cylinder as an indication of depth. The rendering we had was a plug-in to OpenSceneGraph using real-time GPU raycasting. The resolution of the voxel volume was 512 by 256 by 256. So this image, we don't show the transparency just to sort of make it clear what we did, and we're using Perlin noise to sort of modulate the opacity and intensity. In the actual image, it looks something more like this once the transparency was enabled, and we also had a Perlin noise generated background image. Now, we varied a lot of different display conditions, and that included head tracking, and it turns out when you're actually doing this head tracking, if you move your head side to side and you can see the edges of the cylinders, you can actually tell which cylinder is in front or the back. After trying different techniques to sort of make that not a visual cue, what we went with in the experiment was to put a polygonal mask that was at 0 parallax to basically block your view no matter how far you moved your head of the edges of the cylinders. So essentially, in the actual experiment, you only had sort of this type of visual seen through the aperture, and you had to judge depth ordering of the cylinders. So the display environment we used was a fish tank VR, also called desktop VR. This used a 1600 by 1050 24-inch display. It was 120 hertz with NVIDIA time multiplex glasses. In the head track condition, we use a fast track Bohemus, and in the non-head track condition, the user's head was held stationary on chin rest. So we did 2 experiments. The first one referred to as depth discrimination. Basically, the question they had to answer was which of two cylinders, each trial indicated a particular pair. They had to decide which one was in front. There was a short exposure time in viewing the volumetric cylinders for that experiment. And the second one, there was a more complicated question. They had to pick which of the 6 cylinders was either the most in front, the most in back, or the most in the middle. So they were asked one of 3 questions per trial, and there was an unlimited amount of time for them to answer that question. So the main independent variable, as I sort of indicated, was display condition. The basics were whether stereo was enabled or disabled and whether there was head motion tracking or not. The main dependent variable was basically their error rate in answering the question. And we also had a pre-questionnaire asking about demographics and daily computer usage and game usage. In between display conditions, we asked the users to subjectively rate their confidence in answering the question, and then we had a post-questionnaire as well. So in experiment 1, each trial had 3 screens. The first screen was just a 2D display, an abstract representation of the 6 cylinders, and we'd randomly highlight one pair, and this was indicating what pair of the actual 3D cylinders the user should attend to, and then determine which was in front or back. That screen was shown for 3 seconds. The 3D volume set was actually shown for only 2 seconds, so in this case the user would have to look at that pair and decide which was in front or back. That screen disappeared after 2 seconds, and they had to pick one of 3 answers. We considered using a first choice with only 2 answers, but in the end we gave them the option to say that they couldn't decide, and they had 5 seconds to make that decision, and they indicated their choice based on a button press. So there were 12 participants. The first 4 display conditions were just stereo or non-stereo with the head tracking enabled or not disabled. In pilot tests, we found that with a short exposure time, not everybody would use the head motion to get extra depth information, so we included 2 more conditions. A kinetic depth effect condition basically automatically rotated about the cylinders about a vertical line about 10 degrees to the left and right over that 2-second period. And then we had those 2 combinations with or without stereo or that kinetic depth disabled. There were 36 trials for each condition, 216 trials total per subject, and Latin squares controlled the depth, the display conditions across different subjects. So the first analysis we looked at was to check for interaction effects between the stereo and all the motion conditions. We found that there was no interaction effect. There was a simple main effect of stereo. The mean for all the stereo conditions error rate was 28, so if they were randomly guessing, you'd expect 50%, versus the non-stereo conditions of 33. The motion conditions did not have a simple main effect overall. Over here we have a plot that showing the range, error rate 25% to about 40%. In general, as somewhat expected, the stereo, if you turn it from off to on, decreased the error rate, so lower values are better. No motion did the worst. Kinetic depth did sort of middle range, and the head motion, which was the head tracking, did the best. We also noticed when we were querying the user on their subjective impression of how confident they were in their answers in between the display conditions, that the students from one of the pools, we had 2 pools, computer science and psychology department. The computer science pool students seemed to be more optimistic about their answers. And we also looked at the pre-questionnaire and found out that, not surprisingly, they had higher reports of playing more 3D computer games. So we decided to look at a potential for a 3-way interaction between stereo motion and those 2 subject pools. And we found out that for the CS students who played more games, essentially there was an effect where the head tracking condition had a error rate that was smaller than the no motion condition, being no head tracking or kinetic depth. And we also found a difference between the head tracking and the kinetic depth. The kinetic depth for them being 29% error rate and head tracking of 18. And so potentially a plausible explanation is that since they played more computer games, they were more used to using sort of structure for motion for getting this type of depth information. But that wasn't, a key variable in our experiment, so it's only a plausible explanation. Let's see. We also did a 1-way ANOVA repeated measures just looking at all the conditions across. And the graph, we basically just ordered them from left to right, from the least error rate to the greatest error rate. Not surprisingly, the stereo plus head tracking did better than the conditions with neither stereo nor motion, stereo only, or head tracking alone. When we looked at the kinetic depth was sort of the auto rotation. Kinetic depth plus stereo did better than the non-stereo, non-motion condition, and these were all statistically significant. Also did better than the stereo alone. When we looked across stereo head tracking and stereo kinetic depth, there was not a significantly different difference between those two. And finally, stereo alone did better than the condition with neither of them. So the next task was a bit more complicated. The user saw only one screen per trial. On the side of this sort of polygonal mask, again, that was at 0 parallax, was numeric labeling for the 6 cylinders, and they were asked one of 3 questions, either which cylinder is most in front, which is most in back, or which is in the middle, and they had to press a numeric key indicating which of those corresponded to that particular question. And in this case, there was an unlimited exposure time, that is to say the users could take as long as they want. In practice, we'll see in a second, they took on around 15 seconds to answer the question. So here we dropped the kinetic depth effect conditions. We just had 4 display conditions, and this is because with the unlimited exposure time, people were using the motion parallax from head motion, and so we wanted to have more trials of the fewer number of conditions. So this gave us about 128 trials total per participant. So just a little bit on the results. Because the middle question, which cylinder in the middle, could be ambiguous because there were 6 cylinders, there could be 2 correct answers. When we figure the sort of overall expected result, if they're randomly guessing, it actually comes out to be about 22% correct and 78% error based on how we distributed the questions. The first thing we did look at was whether the question, which of those 3 questions had an interaction effect, and the answer was it did not have an interaction effect between the stereo and motion conditions. When we looked at the 2-way repeated measures ANOVA, there was no interaction between stereo and motion. There was a simple main effect of stereo and also a simple main effect of motion. Again, the averages for stereo being 41% error versus 55 for non-stereo, and for the main effect of motion, it was 45 for motion and 51 for no motion. And the graphs over here sort of indicate the qualitative trends you might expect. There was no significant effect on response time, but in general, they varied from about 12 seconds to 15 seconds. There were some interesting trends there. Possibly experiment with more statistical power might actually tease out some results, but we didn't find any statistical significant ones. If we looked at things just as a one-way ANOVA, things sort of fell out more or less the way you'd expect, in the sense that stereo plus head tracking was better than the other 4 conditions. Although interestingly, on the individual case, stereo alone was better than the non-stereo, non-head tracking case. The other cases were not significant. And again, not surprisingly, the response time came out with no main effects. So to conclude, essentially, what we found was that in both experiments, the stereo enhanced the user's depth perception on this particular 3D volumetric data set. Across the 2 experiments, in experiment 2, head tracking had a positive differential effect, whereas in experiment 1, there was this sort of group of students who had more gaming experience. They did seem to get some differential effect of head tracking, whereas the other group that had less gaming experience did not. And finally, as you might sort of expected, the combination of stereo plus head tracking was proved to be sort of the best condition for both experiments across all participants. And in the paper, we also go into a bit more detail about how some of these results compare to some prior work that was studying not volumetric data, but looking at 3-dimensional networks and deciding whether 2 nodes were connected or not. In general, the qualitative results tend to be sort of similar, but they differed in certain areas, which seems to more or less indicate that, as you might expect, making judgments about volumetric data is a bit harder than 3D networks, but it's covered in a bit more detail in the discussion section of the paper. that's it. I'll take any questions.
Okay. Thank you very much.